Today we're going to introduce the VSEPR theory. VSEPR stands for valence shell electron pair repulsion, or in other words, VSEPR or VSEPR. And so the VSEPR theory gives us a 3D, three-dimensional representation of the Lewis dot structures that we've been drawing earlier this week. And so just a preface, as we go through the slides, there will be a lot of information. There are 13 different shapes that you need to know for the AP chemistry exam, 13 different three-dimensional shapes. There is a method to it, and it'll be easier. Please don't be like me 25 years ago where I didn't spend the time to memorize these or to learn these, and then I didn't quite understand what was going on. So please follow along, and I'll try to make it as easy as possible for you. All right, so just a few naming conventions when we take a look here. So the A represents the central atom. The X represents how many bonds there are. Sigma bonds are just like the first bond, the first line, like a single bond. And then the E represents the number of lone pairs on the central atom. And then the sum of X plus E, or the number of bonds plus the number of lone pairs on the central atom, that's represents the steric number. Now, all of those are abstract things, so let's go ahead and go on to the next one. The first thing that we have is a AX. Now, you don't need to memorize the A and the X, just kind of know the pattern or note the pattern. Or so here we have a molecule with two atoms, and we only have one ligand. A ligand is just a code word for bond. So we have one bond, and we don't care about the lone pairs because just 2 points make a line. And so the angle for the bond angle would be 180 degrees, or it'd just be a line here. And so an example could be like HCl, has a single bond, 2 points make a line. So the shape of HCl is linear, just like O2. O2 is also linear because there's only two atoms there. Now let's move on. Now we have a molecule here with a central atom and then two atoms on the outside. So if we take a look at the central atom only, because according to VSEPR, we're only looking at the central atom, it has two ligands. It has one bond here and one bond here. So if we have two ligands and then there's no lone pairs here, so like an example could be like BeCl2, where we have two bonds and we have no lone pairs, then if we add up the number of bonds, which is two, or ligands, and the number of lone pairs on the middle atom, the central atom, is 0. So 2 plus 0 gets us the steric number, so that's 2. So if we take a look here, we have no lone pairs, so they don't repulse. And we just have the repulsion from those electrons. And the electrons want to be as far apart from each other as possible in those two bonds. And so that's why the shape of this is going to be linear. And the angle would be 180 degrees. So if we take a look here, the angle between here to here would be 180 degrees. And then that's like the angle that's given to us there. All right, now going on to the next one. Here we have AX3, which means that we have one central atom, and then we have three bonded atoms. So we have X's here. Now the X's could be different atoms or different elements, and that's okay too. Now, if you take a look at the drawing, they have a line here, and they have a little dashed line. The dashed line means that it's kind of the drawing, the 3D drawing is going back into the page. And then over here, then this little wedge means that it's coming out of the page. Now for trigonal planar, it's actually similar to like the letter Y. So if we had like this in our page, and then we had the central atom here, and then we had an external atom here, and then we also had another external atom here, and we had an external atom here on the bottom. We have the three bonds, and they're all spaced equally apart. And if we tried to figure out where the bond angle is, well, if we take a look at the bond angle between here to here, if it's equally spaced, should be 120 degrees. Between here to here should be 120 degrees. And between here to here should also be 120 degrees. So they're all equally spaced. So think about the name trigonal, which means 3. So we have 3 X's. And then planar, just like in geometry, is in a plane. So like on our paper. And so this would be the shape of trigonal planar because the bonds are all as far apart from each other as possible. The electron pairs in the bonds are far away from each other. So we have 3 ligands, no lone pairs, so the steric number is 3. So the bond angle should be 120 degrees like we've drawn here. All right, then we move on. Let's go to the next one. We have 2 ligands and we have 1 lone pair. So the lone pair is represented by the letter E. So imagine if you had the lone pair here, and what's going to happen is the lone pair is going to push down on those electron pairs in those 2 bonds. And so instead of being linear, like we had the AX2 from before, and so I want to draw AX2 just so you remember kind of what it looks like. AX2, remember, was linear because there were no lone pairs pushing on any of those. But if we take a look here, then what happens is with this particular one, we have the lone pairs and they're pushing down on it. And so what happens is instead of being a straight line, now the shape of this is really bent. And so if we take a look at bent, then it's not equal to 180 degrees for its bond angle. So we have a little difference here. So let's go ahead and take a look and see what goes on over here. So if we take a look here, we actually have a bond angle down here of less than 120 degrees. So it's about 116 degrees, like it says over there. So it's a little less than what it would be for trigonal planar. And so it would be 116 degrees. And so what happens is in real life, what do you see? Well, here, let's go ahead and clear the drawings. And we take a look. We wouldn't see the lone pair. And so what we would really see is what this part is. We would see the bent shape. We wouldn't see this because this is a lone pair here. And so the lone pair would just be part of the central atom that we have here. And so we really see a bent shape. And so that's the reason why up here it says that the shape of this is bent. The next shape is tetrahedral. So we have central atom and then we have 4 atoms bonded to it with no lone pairs. And so all of them in 3D shape look like a jack. So it's tetrahedral. So the bond angle should be 109.5 between each of these. Now keep in mind, this is 3-dimensional, not like 2-dimensional like on our paper. If we drew CH4, it would look like it's a 90-degree angle on the paper. But remember, this is 3D where some of them are coming out of the page, some of them are behind. So if you think of like a jack, like a ball and jack, like the old school game from like the mid 1900s, I guess. I don't know, something like that. Anyways, you can Google ball and jack or jack game. I don't know, maybe. And then you can find what it looks like. They're equally spaced. Then with the same steric number as the tetrahedral one, we also have something called trigonal pyramidal, where we have 3 bonds and then we have 1 lone pair. And so if we take a look here and we omit, or if you imagine that the lone pair is not there, the lone pair is pushing down on each of those bonds. And what happens is then you get a trigonal pyramidal. So you get a triangular pyramid shape. And that's what happens when you have ammonia, NH3. And then the same thing here, then also the same steric number, except with 2 bonds, like in water, and 2 lone pairs on the oxygen, like in water. Then what happens is those lone pairs push down. And so that's the reason why water shape is bent. It still looks tetrahedral in its electron pair geometry. It still has 4 pairs of electrons, but we just don't see 2 of them in real life in the shape. And so we see a bent shape here. Now for each of these, if we take a look at tetrahedral, the bond angle is 109.5 perfectly. Then when you add a lone pair with the same steric number, the bond angle becomes a little less than the ideal 109.5. So trigonal pyramidal has a bond angle approximately 107 degrees. And then the bent bond angle is approximately 104.5, which is even less because the electron pairs or the lone pairs have a little extra push or repulsion on those bonds. And so those are all the ones with steric number 4. Then we'll notice the pattern with steric number 5, trigonal pyramidal, trigonal bipyramidal. The prefix tri means 3, bi means 2, 3 plus 2 is 5. And so this is when we break the octet rule or expand the octet, then we get these shapes. And so if we have 5 bonded atoms here with no lone pairs, then this would be trigonal bipyramidal, where each of these in the plane that we have here are 120 degrees bond angle between those. And then between the ones in the plane to the ones on the bottom, those bond angles are 90 degrees, and those would be equally spread out. Now keep in mind, all the subsequent ones with steric number 5, imagine if instead of an X, we had an electron pair here. Those would take the place of each of these, but you would still see what's left. So the next shape, if we go on, we'll still have a steric number 5, and that's seesaw, where we have 4 bonds, so see 4 X's here, and then we have 1 lone pair. So the 1 lone pair will push down, and then you're left with a seesaw shape. So keep in mind, if you imagine this like a seesaw at the playground, one of them is coming out of the paper with this wedge, and then the dashed line is going back into the paper. So think of these as being perpendicular to each other, and then you have those there. So think of a seesaw. These are the legs, and this is the board. Now going back, if we turn this sideways, or you turn it sideways, make this X the lone pair, and what do you see? You see the seesaw. That's on this page. All right, then what we do is let's add another lone pair. So now we'll substitute another one of these X's or bonded atoms, and we'll put another lone pair there. And now we get T-shaped. So if we take a look here, imagine these being the legs of that seesaw. Now there are lone pairs. What are we left with? We're left with the T. And so this is T-shaped when we have 3 ligands and 2 lone pairs on the central atom. Then going on to the next one, we have the last one is linear. So we have 2 ligands and we have 3 lone pairs. And then we would have a linear shape. And then going on, then the last set for the AP exam would be the ones with steric number 6. So we take a look at like SF6. This has 6 bonded atoms to it. So 6 plus 0 lone pairs on the central atom gets us a steric number 6. And so all these would be 90-degree angle separated from each other. So this would be octahedral. And now the variation then of octahedral, if we substitute in a lone pair here for one of those bonded atoms, like we did on the bottom here, then we would have square pyramidal, where we have a square in a plane, but the pyramid makes it so if we connect to the top, and I can go ahead and let's go ahead and draw those in just so we can see. So we'd have a pyramid, and then we'd have a square. Oops. We'd have a square in there, and then that's how you get the square pyramidal. All right, and then the last shape that you need to know for the AP exam is the last one. Now, if we had 2 lone pairs and 4 ligands, the lone pairs would be on the top and the bottom, and then this would be square planar. And so if we take a look here, we put one here, connect the dots, connect the lines, connect those, and then we have a square in a plane. And then I know it looks like a rectangle, but trust me, it's square pyramidal, and the angle is 90 degrees. Where the lone pairs, there's one on top and one on the bottom, they're pressing equally. All right, and then some kids just wanted to know, but you don't need to know for the AP exam. Is there a steric number of 7? Yes, there is. That's pentagonal bipyramidal. Penta is 5, bi is 2, 5 plus 2 is 7. And this exists, but you don't need to know this one for the AP exam. All right, so the information that I just gave is on this slide. If you need to take some notes here, you can take a note. It does have a couple of things to point out, is that the number of ligands plus the number of lone pairs always equals the steric number. So I'll put that on here. 2 plus 0 would equal 2. So if you take a look at each of these, 4 plus 0 equals 4. 3 plus 1 equals 4. Another pattern to note is that if you take a look here, all the ones with the steric number 3 have the same electron pair geometry. Electron pair geometry tells you, including the lone pairs and including the bonded atoms, how the electrons would be arranged or how those electron pairs would be arranged. So all those with a 4 for the steric number would have a tetrahedral electron pair geometry and almost the same bond angle, almost 109.5 or 109.5 or around that. And then hybridization we'll get to a little later, and I'll save that for another video just to save a little time. And then the shapes, like we talked about, these are the 3D shapes that you would see like we've gone over on the slides. The extra ones that we had here, so all the ones seesaw, T-shaped, linear, they're all here too. I'll make sure that the notes are in there for you. Just another way of organizing them. So if we have a steric number 2 and no lone pairs, then the shape should be linear. If you had a steric number 3 and you had no lone pairs, it'd be trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. So with the no lone pairs, these are the shapes. And then all the variations, depending on the steric number, they're all listed here. So there is a pattern. However you remember them, please try figure them out. Tomorrow we'll do a little practice applying this. We'll draw some Lutz dot structures, and then we'll see if we can figure out which shape it is.